So when I was talking about energy in the last video, we're mostly looking at large objects, but now I want you to think very small and think about the atoms or the molecules that make up those objects. If you have an object that's at a fairly low temperature, the atoms or the molecules are not going to be moving very fast. They might only just vibrate in place. In fact, anything that's a solid, they're just vibrating in place. If you get the solid warmer, they'll vibrate even more. And if you get the solid even warmer, they'll vibrate even more. And eventually, if you get it warm enough, you get to that thing we call the melting point, where instead of just vibrating in place, now they've got enough energy that they can start moving around each other. What I want you to know here is that that whole thing about moving, remember, is connected to this idea of kinetic energy. So when we think of the temperature of something, we have to think about its molecules, and we have to think about those molecules moving. So kinetic energy of molecules or atoms is what determines the temperature. And it's really the only thing that determines the temperature. So the temperature of something is just the average amount of kinetic energy that the molecules have. Now, not every molecule in a substance is going to have the same exact amount of kinetic energy. If those molecules are moving around and banging into each other, one might be going a little bit more slowly, and then it hits something else, and after that it gets some more energy and it goes faster, and they're all different motions in there, but the average of the amount of kinetic energy that each different molecule or atom has is what we relate to temperature. Now, you are familiar with the Fahrenheit scale, which is what we usually use here in America. Most of the world uses the Celsius scale, and that's what we always use in the laboratory. Celsius scale. There's another scale called the Kelvin scale, and that becomes very, very useful because Lord Kelvin decided that there needed to be a scale where 0 represented no energy at all. And that's considered or called absolute zero. So 0 on the Kelvin scale is called absolute zero, and they call it that because if something is at absolute zero, it really has no energy at all. Now, we've not been able to make that happen here on Earth. It's so hard to get all the energy out of something, so we don't even know what would happen to matter if you took all the energy out, because it would mean that the molecules and atoms couldn't move anymore, but it would also mean that even the electrons couldn't move anymore. So we have no idea what happens to matter if you do that to it. Maybe somewhere out in deep space there is matter at absolute zero, but we don't know about that. But these two scales are related to each other very easily, thankfully, where degrees Celsius is equal to kelvins. Notice that kelvins does not use a degree sign, it's just kelvins. Kelvins minus 273, and we can write that differently and say that Kelvin is equal to the degrees Celsius plus 273. So kelvins are always a bigger number because it has to start at 0. It can't go below 0. So if you think of something at 0 degrees Celsius, that's the freezing point of water. Well, the freezing point of water on the Kelvin scale is 273. So if you said the water is frozen, what temperature is it at? You'd say, oh, it's at 273 Kelvin. But it's at 0 Celsius and, of course, 32 Fahrenheit. So these are the formulas that you would use to convert Celsius into Kelvin, or vice versa.